Hello, Mr. Stone here, and we are going to look today at chi-squared tests, which are really going to answer the question, are sets of data independent from each other? There is a way that we can tell this rather than eyeballing it, and we can do it to a certain degree of accuracy as well. So let's look at some voting records. So let's say this is the record of voting for a particular election, broken down by gender. We have men, women, they are voting for three parties: Republican, Democrat, or Minotaur. Minotaur being the mythical beast that has the head of a human and the body of a man. I said that wrong. It's actually the head of a bull. There we go, like that, and they're quite scary. And the scary, ooh, and the body of a man. All right. Um, so this is another hypothesis testing situation. So we are going to have H naught and HA for our null and our alternative hypothesis. H naught is basically going to say that's your null hypothesis, that the sets are independent. They have nothing really to do with each other. Independent. And then our alternative hypothesis is just to say that these sets are not independent. So in this case, the first thing we should do is come up with an alternative and null hypothesis for this data set. And my null hypothesis is going to be, well, I'm going to talk about two things being independent here. The sets, I've got voting and I've got gender. So I would say that voting is independent, or voting records quite technically, is independent of gender. And the alternative hypothesis is that voting is what? Not independent of gender. Two things that are mutually exclusive, cannot be independent and not independent. All right. To go further here, what we're going to need are totals. So we need to get some totals for these columns and some totals for the rows as well. So 56 and 45, well, that is 101. Sometimes you'll be given this. Quite often, though, you'll have to figure it out yourself. 38 plus 54, haha, that is 92. 6 plus 1, that was 7 last time I checked. 56, 38, and 6 all add up to 100. And 45, 54, and 1 also add up to 100 as well. All right, so we will need our totals here. We just had some totals there. We had some totals here. Oh, and let's get a total of all our totals. Either way you add it up, if you go down or if you come across the row there, you'll get a total of 200 people are included in this particular data set. And now we need to get our chi-squared. And chi-squared, it actually kind of looks like a curvy kind of X there. But our chi-squared is going to be this guy right here, that is sigma, that's your sum of a bunch of stuff. So we're going to take the sum of everything. We see that that's there means we're going to take the sum of everything of our observed versus our expected results. Okay, so the observed is what we just saw. That is what we've got. This expected, though, well, if it is broken down fairly and the two data sets truly are independent, we're not going to really see any difference between the two. So we should expect to see that they are the same. So how do we figure that out? Well, we're going to take our totals down here. So let's take a look at my expected number of men who would vote Republican. I'll give them a big R. Okay. I see that I've got 101 people that voted for Republican, and I've got 100 men that totally voted. And that's over here. So what I would do is I would just take those two things times each other, 101 times 100, and then divide that by the total number. Divide that by 200, and that will give me 50.5. So this is the expected number that I would expect to see. Whoop, I can't move my screen all of a sudden. Wow, okay, there we go. Expected number men to vote Republican, and I just put that there. I just like writing things twice sometimes. Sometimes it's just a nice thing to do. Similarly, I could expect the number of men to vote D for Democrat. I've got 92 is my total number of voters for Democrat. I've got 100 again. I'm going to use that same 100 because I've still got 100 men. Divide by, I've still got 200 people total. So 92 times 100 divided by 200 will just give us 46. Okay, we're going to do the same thing again. You just take the total. If I want to get my expected number of Republican men who vote Republican, I would just take my total number of that column times the total number of the row times each other, and then divide it by my total number of people that I've got in my survey in this case. All right, so I can do that, and I will come up with expected values for all of these. And it would actually look something like this. So I've got men, I've got women, and I've got Republican, I've got Democrat, and I've got Minotaur. I would expect to see 50.5. I would expect to see 46. And I would also expect for the Minotaur party, I would expect to see 3.5. And if this is independent of gender, then I should expect to see the same thing in both. So we're going to see that 50.5 is there as well. 46 is there, as is 3.5. If they truly are independent of gender, then aside from some minor fluctuation, we should expect to see two people voting for the same and all those things. So this is our expected values. And here's what we're going to do once we've got those. We need to use these expected values in here for each individual value that we've got. And then underneath that we divide by the number of expected. So let me break down one of these examples here. Okay, so I would, in this first case here, I'm going to use this 50.5. Okay. So I saw that the actual number, observed number, were 56 men voted Republican. So I would have 56, this is my observed number, okay, minus my expected, which we calculated out to be 50.5, and this is going to be squared. Divide that by the expected number that's going to go on the bottom, and so we're just going to repeat here this 50.5. Okay? So when we do that, we would get something that looks like this. Okay, so this is just going to go down right there. I'm going to do the same process for every one of the values in my table. Okay, I need to do that. I've got 6 things that are up here. Okay, so I should have 6 things I'm added together, and I even set them out kind of similarly to what we saw in the table. Okay, so I've got 3 on top, 3 on the bottom, just because, you know, hey, that looks kind of neat. That kind of reminds me of that table that I just had. 6 things, 6 calculations. I calculate all these out, and again, I set them up kind of the same way here. 0.599, 1.391, 1.786. Hey, they repeat in the bottom because, as I said, if they are truly going to be independent of gender, the results, then they should be the same. The gender should have no difference to it. Add them all up. That is our chi-squared value. In this case, that is 7.552. Okay, now we need to think about degrees of freedom. So degrees of freedom for when we are doing chi-squared tests, it's your number of rows minus 1 times your number of columns minus 1. Well, we had 2 rows minus 1 times, we had 3 columns because we had Republican, Democrat, and the mythological beast, the Minotaur Party. 3 minus 1, which is, I don't know, I would never vote for a mythological beast, but hey, you know what? It's a free country. We can vote for whoever we so wish. We calculate this out. Well, 2 minus 1, last time I checked that was 1. 3 minus 1, hey, last time I checked that was 2. 1 times 2 is 2. So we have a 2 degrees of freedom. Now we're going to take this 2 degrees of freedom, we're going to look on our table of chi-square distribution, and we're going to get a critical value. And in this case, we're concerned with, we're going to have a p-value here again. We're going to use p of 0.05. So we're going to look up a chi-squared. Chi-squared of 0.05. Look that up on your table. In this case, with 2 degrees of freedom and a chi-squared of 0.05, we would be looking for 5.991 to be our critical value. Yay, critical value. We're almost there. Just bear with me. Critical value of 5.991. So, if our chi-squared that we calculated is greater than the critical value, we reject our null hypothesis. If chi-squared is less than or equal to our critical value, we do not reject our null hypothesis. So we saw that the chi-squared that we had was 7.552. Our critical value here is 5.991. So 7.552 is greater than 5.991. So we're going to go up to here. This is the case in this particular instance. Our chi-squared, 7.552, is greater than 5.991. Therefore, we reject the null hypothesis. Okay, so we reject the null hypothesis. We got that. All right. Let's go back up. What was our null hypothesis? Well, if we go back to the very beginning up here, we said that our null hypothesis is that voting is independent of gender. And we said that we're going to reject that, so we do not buy that in this case because our chi-squared is too high. So we're inclined to believe that this is the case right here, that voting is not independent of gender, and although your results may vary depending on what type of election you're looking at, in this particular election, we can say with some confidence that gender is not independent from voting habits, and that tells us something a little bit about the results of how people voted here, and maybe that can be used when you're analyzing this election and future elections going forward. People that are campaign managers can think about this. People can think about the importance of the issues to various groups that are participating, and it applies in this, and it can apply in a whole variety of other uses as well. So there is a lot of stuff going on in here. There are a fair number of moving parts. We will practice this some more, but please feel free to go back, look at those parts that look a little bit and we will talk and practice. All right. Thank you for listening. Have a wonderful day.